So now let's take a look at uncertainty and error. So there's mainly two type of uncertainty: systematic and random error. Systematic is consistent and it's a consistent error. So for example, if you use a ruler to measure the length of the book, the ruler itself may contain some uncertainty, and the uncertainty is consistent. And this is an example of systematic error. The second type is random error. So random error is error caused by unknown and unpredictable change in the experiment, and this change may occur in the measuring instrument or in the environmental conditions. So for example, if you want to record the amount of time for a student to run 100 meters, you might start the timer a little bit earlier or a little bit later, and this cause some inaccuracy in the result, and this is a random error because it's human error. So how do we make sure the accuracy of result and reduce random error? The first thing you can do is do a multiple trial of experiment. That's why when you are doing a lab report, you probably have a lot of data because you wanna try to reduce the impact of random error, and then you usually take an average volume of multiple trials of data to get a more precise, more accurate estimate of the result. And then in experiment, you need to include uncertainty as well. So when you are measuring something, there's usually a reading uncertainty, and reading uncertainty is equal to half of its smallest precision, and precision refers to the closeness of two or more measurements to each other. So reading uncertainty is always read in the way of best estimate plus or minus uncertainty. So, and just be careful that you always have to run the experimental measurement or the result to the same decimal places as the uncertainty. So if I say 54.6 milliliters plus or minus 0.05 milliliter is not correct because the uncertainty has two decimal places and the best estimate only has one decimal places. So I have to change the result to 54.60 milliliters plus or minus 0.05 milliliter, and that will be the correct answer. And here show you another example, like 1.237 second plus 0.1 second is not correct because the uncertainty only has one decimal place, and the best estimate has three decimal places. So you have to change the decimal place of the estimate to one places. So this is a reading uncertainty example. So the picture on the left shows you the volume of a blue liquid, and the reading of the liquid is somewhere between 165 and 200 milliliters. So the smallest precision is 25 milliliters. So the uncertainty will be equal to half of the smallest precision. So we just use 25 divided by 2 is equal to 12.25 milliliters, and this will be the uncertainty for this problem. And then we need to take the average volume of the liquid. So the average volume will be equal to 175 plus 200 divided by 2, which give us 187.50 milliliters. And then we need to include the uncertainty as well. So the reading will be 186 milliliters plus or minus 12.24 milliliters, and that will be the final answer for this problem. So this is a uncertainty table. Usually ruler has a uncertainty of 0.05 milliliters, and vernier caliper has a uncertainty of 0.05 milliliters as well. Micrometer usually has a uncertainty of 0.0005 milliliters, but just be careful. The uncertainty may change depends on your measurement too. This table just shows you the frequent situation, but still be careful when you are measuring something. So now we are going to talk about accuracy and precision. So accuracy is how close your volume, the actual volume, is to the true volume or the theoretical volume, and precision is how close to measurement is. So the picture on the left shows you the difference between accuracy and precision. So this picture, the picture on the left up corner, has both high accuracy and precision, and the picture on the left bottom corner it only has a high accuracy but low precision. And then this picture, the picture on the right corner, has a low accuracy and high precision, because you can see like all those black dots, they are very close to each other, so meaning that they have a very high precision. In the picture on the right bottom corner, this has a low accuracy and low precision, because like the all black dots are spreading out, meaning they have a low precision and they are not very concentrated on the centers, so they also have a very low accuracy. So now let's take a look of how to calculate average volume and uncertainty. So average volume is also known as mean volume and is equal to sum of all terms divided by number of terms. And uncertainty is equal to the maximum volume minus the minimum volume divided by 2. So let's take a look at an example. So assume you measure the length of a string and you measure it for 10 times, and you list the volume on a table, and this is the volume of your measurement, and then the average volume will be the sum of the term divided by the number of terms. So we have 10 volumes, so we divided by 10, and then the average volume will be equal to 169.8 centimeters. And then we need to calculate the uncertainty. So uncertainty is equal to the maximum volume, 195, minus the minimum volume, 124, and then divided by 2, which give us 35.5 centimeters, and then the result will be written as 169.8 centimeters plus or minus 35.5 centimeters. So this is another example. I know there's a lot of data, but just try to calculate them so that you can have a really solid understanding of uncertainty. So this table shows you some pressure, and try to calculate the average volume and the uncertainty. So pause the video and calculate them first by yourself. Alright, so now I'm going to go through the answer. So in order to find the uncertainty, I need to know the maximum pressure first, and then I need to know the minimum pressure, and then I subtract the minimum pressure from the maximum pressure, and then divided by 2, in which give us the uncertainty, and then I will plus all the pressure together, and then divided by the number of term, which is 4. Actually it's 3, which give us a average pressure. So there's also different type of uncertainty. So there's a frictional uncertainty, percentage uncertainty, and the absolute uncertainty. So for the number 0.4 centimeters, this will be the absolute uncertainty, and the number 28.3 will be the best estimate. So absolute uncertainty over mean volume will be equal to the fractional uncertainty. So in this case is equal to 0.4 over 28.3, which give us 0.0140, and this will be the fractional uncertainty. So percentage uncertainty is equal to your fractional uncertainty times 100%. So in the case, it gives us 1.40%. So in general, when we express all of those uncertainty in terms, that's how we wrote it. Just so delta A is absolute uncertainty, and fractional uncertainty is equal to delta A over A, and percentage uncertainty is equal to delta A over A times 100%. And A is the best estimate, and delta A is the uncertainty, actually the absolute uncertainty. So how do we calculate uncertainty? In this part, I will show is about the addition and subtraction. So I summarized them into calculate the estimate volume and then plus or minus our uncertainty, absolute uncertainty. So for example, if A is equal to 3.56 plus or minus 0.23, and B is equal to 193.3534 plus or minus 2.24. How do we calculate A plus B? So just add up all the estimate volume and then calculate the absolute uncertainty. And for B minus A, same thing. You just calculate the estimate volume first. You subtract 3.56 from 193.34, and then you calculate the absolute uncertainty. Multiplication and division. I know this seems a little bit complicated, but it's actually not that hard. So let's assume Q is equal to A times B. So the delta Q over Q naught is equal to delta A over A naught plus delta B over B naught. So I will just do some examples so you guys can really understand what all of those letter means. The side of a rectangle is measured to be 2.5 centimeters plus or minus 0.1 centimeters, and B is equal to 5.0 centimeters plus or minus 0.1 centimeters. Find the area A of the rectangle. So pause the video and try this number first by yourself. So now I am going to go over the problem. So to find the area of the rectangle, we need to calculate the uncertainty of the area. So the first thing we need to do is we need to calculate the fractional uncertainty of A, which is equal to delta A over A naught. Delta A is the absolute uncertainty, and A naught is the estimate volume. So in this case, is equal to 0.1 over 2.5, giving us 0.04, and then the fractional uncertainty of delta B is equal to 0.1 over 5.0, giving us 0.02, and then we need to calculate the fractional uncertainty of area. So you just plus the fractional uncertainty of A, and then plus the fractional uncertainty of A, and then plus the fractional uncertainty of B. So it's equal to 0.04 plus 0.02, giving us 0.06. And now we need to calculate the area A naught of the rectangle, which is equal to 12.5 square centimeters. And then to find the fractional uncertainty of A naught, we will multiply 12.5 square centimeters by 0.06, which give us 0.75 square centimeters. So the final answer of this problem is 12.5 square centimeters plus or minus 0.75 centimeters. Square centimeters, I mean. Power and root. So if q is equal to a to the b's power, then the delta q over q naught is equal to the absolute volume of, this should be the absolute volume of b times delta a over p a naught. And then if it's a square root, delta q over q naught will be equal to 1 over the absolute of n times delta a over a naught. The length of a simple pendulum L is increased by 4%. What is the fractional? I spelled the vocabulary wrong. What's the fractional increase in the pendulum's purity, giving that period is equal to 2 pi times the square root of L over g. G is a gravitational acceleration by Earth, is equal to 9.81 meters per second squared. So pause the video and try this problem by yourself first. Alright, so now I am going to go over the problem. So I will provide some actual practice problem in my website, and I will post the link of this presentation and the practice problem in the description as well. This is a reference for this presentation. This include like all the sources of image in the problems. And thank you guys for watching this video, and I hope this can be helpful for you. Please subscribe my channel if you like it, and follow my website.